Imagine a heart the size of a city, a sphere of crushed matter only 12 miles wide, spinning rapidly in the absolute darkness of deep space. It is not made of flesh and blood. It is made of neutrons, packed so tightly that a single teaspoon of this material would weigh 1 billion tons. And it is beating, not with a pulse of blood, but with a pulse of pure high-energy radiation, sweeping across the galaxy like a lighthouse beam, 3 times every single second. This is not a metaphor. This is the reality of a dead star. But specifically, we are talking about one star that refused to follow the rules. A star that exploded, died, and then began to exhibit a split personality that has baffled astronomers and rewritten the textbooks on stellar evolution. This is the story of PSR J1846-0258, a star that proves the universe is far stranger than we ever imagined. To understand why this object is so important, we first have to understand the violence of its birth. A few hundred years ago, in the constellation of Aquila, a massive star reached the end of its life. It ran out of nuclear fuel. In a fraction of a second, its core collapsed under its own immense gravity. The outer layers were blasted into space in a supernova explosion, leaving behind a beautiful, expanding cloud of gas and dust, known today as Kesteven 75, or KES 75. Inside that colorful nebula, the core of the star survived. It was crushed down into a neutron star. For decades, astronomers divided these neutron stars into 2 distinct families. On one side, the pulsars, the reliable clocks of the universe. They spin rapidly, powered by their rotation, emitting steady, rhythmic beams of radio waves and X-rays. Stable, predictable, and remarkably precise. On the other side, the magnetars, the monsters. Neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Chaotic, violent, prone to unpredictable outbursts of gamma rays and X-rays. They spin more slowly and are powered not by rotation, but by the decay of their enormous magnetic fields. For a long time, scientists thought these were 2 different animals. A star became a pulsar, or it became a magnetar. But then we looked deeper into the heart of KES 75. We found a pulsar there, PSR J1846-0258. At first glance, it looked like a classic rotation-powered pulsar. It was spinning roughly 3.1 times per second. It emitted strong X-rays. It powered a pulsar wind nebula around it. Astronomers measured its spin-down rate, the rate at which it slows over time, and calculated its age. It was young, only a few hundred years old, making it one of the youngest pulsars in the Milky Way. Everything seemed to fit the standard story. But then came the problem: a ghost in the numbers. When physicists calculated the strength of its magnetic field from how fast it was slowing down, they got a number that didn't make sense for a normal pulsar. About 4.9 times 10 to the power of 13 Gauss. Almost 50 trillion Gauss. Dangerously close to the magnetar regime. Yet the star was behaving calmly. It was a wolf in sheep's clothing, the engine of a pulsar with the magnetic skeleton of a magnetar. Astronomers suspected it might be the missing evolutionary link, but they needed proof. And then, in June of 2006, the universe provided it. The Rossi X-ray Timing Explorer detected a series of violent, magnetar-like bursts coming from KES 75. These were not regular pulsar pulses. They were magnetar bursts, short flashes of energy shining hundreds of thousands of times brighter than the sun, releasing in 1/10 of a second as much energy as our star emits in many hours. At the same time, the pulsar glitched. Its rotation suddenly sped up, a hallmark of extreme internal stress, usually associated with magnetars. Its spectrum changed. It brightened. There was no longer any doubt. PSR J1846-0258 was a hybrid, a high magnetic field pulsar capable of magnetar behavior. This event broke the old classification. It proved there is no rigid wall between pulsars and magnetars. Instead, they lie on a continuum. A high-field pulsar can evolve into a magnetar, or temporarily behave like one when its magnetic field reconfigures. But the science goes deeper. One of the most important clues comes from a quantity called the breaking index. It measures how a pulsar's rotation slows over time. If a neutron star were a perfect magnetic dipole radiating into a vacuum, the breaking index would be exactly n equals 3. But when astronomers measured PSR J1846-0258, they found n approximately 2.65 before the 2006 outburst. And afterward, when the magnetic field had reorganized itself during the flare, the breaking index dropped even further, n approximately 2.2. In astrophysics, this difference is enormous. It means the star is not slowing down just through simple dipole radiation. Something else is happening, perhaps a powerful particle wind, or a magnetic field that is evolving in real time. This is one of the clearest hints that magnetar-like processes are at work beneath the surface. The environment of the star adds even more context. Because PSR J1846-0258 is so young, it is still deeply embedded in the expanding debris of its own supernova, KES 75. By studying the chemistry of the remnant and how the pulsar's wind interacts with the gas, astronomers can reconstruct the timeline and energies of the original explosion. This object also forces us to rethink where magnetars come from. One leading idea is that magnetars are born when a stellar core collapses while spinning extremely fast, creating a dynamo that amplifies the magnetic field to unbelievable strengths. PSR J1846-0258 may sit right on that borderline, born with a massive magnetic field, but not quite massive enough to behave like a full magnetar all the time. It is a cosmic in-between state. Since the 2006 burst, the star has quieted, returning to its pulsar-like rhythm. But we now know what lurks beneath the surface. We know the magnetic field can snap again. We know the crust can crack again. We know the star can switch personalities in an instant. It teaches us that neutron stars, the densest objects in the universe after black holes, are not static relics. They are dynamic, evolving, active. And we only see this object at all because we built instruments capable of seeing through dust in X-rays, observatories like Chandra and the Rossi Timing Explorer. Without them, PSR J1846-0258 would be invisible, hidden behind the dust of the galactic plane nearly 20,000 light-years away. So what does this mean for the bigger picture? It means neutron stars are far more diverse than we thought. There may be hundreds of sleeping magnetars masquerading as pulsars, each capable of waking violently. It means magnetic fields are the real architects of a neutron star's life. PSR J1846-0258 is a zombie star, born in death, spinning in the darkness, holding a magnetic field that defies comprehension. A pulsar that remembers it wants to be a magnetar. The next time you look toward the constellation Aquila, remember, hidden in that darkness is a city-sized sphere of neutrons, spinning 3 times a second, building tension in its magnetic skeleton, waiting for the next moment to scream energy into the void. It is the star that exploded, kept beating, and refused to be categorized. If you are captivated by the extreme physics of this hybrid star, hit the like button and subscribe. Thanks for watching, and keep looking up. Veil Origins. Impossible Truths.